properties of these ionic liquids are, as we know, the various volatile organic solvents we are using in the synthesis, and which has the problem of, the environment. The volatile solvents are not, environment friendly, and also they have some toxic effects or hazardous effects are there. So in order to overcome these problems, these ionic liquids were studied. The room temperature ionic liquids, that means it is the category of ionic liquids which is at room temperature exists in the liquid phase. So these are the salts that are liquid over a wide range of temperature, including the room temperature, like from -40 degree to plus 100 degrees Celsius. It is existing, what you can say, the liquid state. So there are the various combinations we can try. The variations in the cations and anions can produce the literally millions of ionic liquids we can use in various applications. So these ionic liquids can be chiral, it can be fluorinated, or some antibacterial ionic liquids are also there. So the large number of possibilities are there which will fine tune the ionic liquid properties for the various applications. The driving force. Why exactly we are moving towards the ionic liquids? So as I said that the chemical industries are basically focusing facing a problem on volatile organic solvents. So as we know, this volatile organic solvents, it can be toxic or hazardous in nature, or sometimes it may cause the serious environmental issues such as atmospheric emissions, contamination of aqueous effluent, and so on. So these solvents, these ionic liquids can be overcome this problem, and so this gives the key step to minimize the waste which is generated by the organic synthesis. So there are the two approaches we can basically consider, that is the greener process and the recycling of the homogeneous catalyst, so that we can reduce the problem which is there of contamination with the aqueous effluents and whatever the waste products which are generated due to the organic synthesis, that we can minimize by using this organic liquids. So it is the important step to minimize the waste in the chemical manufacturing process by substituting the ionic liquids, which will have the atom efficiency as well as the catalytic alternatives in the synthesis. Now, as I said, the green chemistry. So what exactly the green chemistry means? As the organic synthesis generates a lot of waste, which is hazardous, and even the solvents which we are using, they are not that much safe. So the ionic liquids have been discussed as a promising solvent for the clean processes as well as for the green chemistry. So by considering these two words, that is green processes and green chemistry and clean process, we can reduce drastically the amount of side and the coupling products, that is whatever the side reactions are there, waste which is generated, that can be minimized. And second, the solvents and the catalyst consumption. The advantage of this ionic liquid is we can reuse these ionic liquids, we can recycle it, and because of the recycling, we can minimize even the cost of the synthesis. Now, why to consider these ionic liquids? So the use of these ionic liquids as the novel reaction media, which may offer a convenient solution to both the solvent emission as well as the catalyst recycling problem. So these ionic liquids are environmentally friendly, alternatives to these organic solvents for the liquid-liquid extraction, catalysis, separation, as well as the electrochemical reactions. The ionic liquids will also reduce the related cost, as I said, as it is recycled and reused again. So ultimately the cost for the catalyst can be reduced. Disposable requirements and the hazards associated with the volatile organic solvents can be minimized due to the use of ionic liquids. The ability to fine-tune the properties of ionic liquids medium will allow the selection of ionic liquids to replace specific solvents in variety of different processes. That means based on the requirement of the synthesis, whether we require the basic medium or whether we require the acidic medium, depending on that, we can modify the ionic liquids easily. So the typical ionic liquids, as I said, that it is simple, the combination of cations and anions. So most widely used ionic liquids contains this imidazolium ion, pyridinium ion, ammonium ion, or phosphonium ions. And for the anionic species, the few examples are tetrafluoroborate, hexafluorophosphate, and so on. Also, along with that, it contains the various halogens like chlorides, fluorides, bromides, and so on. So among these various known ionic liquids, which are having the quaternary ammonium structure as well as the phosphonium salt, shows the wide range of applications, including the organic synthesis as well as the biphasic catalysis reaction, and also in the many areas such as the surfactants, electrochemistry, separations, and the phytochemistry. Ionic liquids are generally, these are the salts of organic cations, such as I said, imidazolium, pyridinium, ammonium, and the anions which are used, halogen, triflate, tetrafluoroborate, and so on. These exist in the liquid state at relatively low temperatures, and the examples of the cations which are used in the preparation of ionic liquids are, so these are the some cations which we can use, that is imidazolium, pyrazolium, triazolium. All these are the heterocyclic nucleus which we can use, and these are the bulky as well as the asymmetric organic cations, because if the chiral cations, always again there is a problem of stereoselectivity. So that's why these asymmetric and bulky cations are used. And along with that, these cations can be combined with the anions, which can be either inorganic anions or organic anions. So these are the examples of inorganic and organic anions like sulfonates, imides, methiide, and wherever the R is there, that R can be halogen, that is chloride, bromide, or fluoride, or CF3, trifluoromethyl, or C2F5, and other all the electron withdrawing aryl or alkyl substituents we can use in the anions. But in that, the PF6 minus, these are used for the moisture stable and water immiscible ionic liquids. So whenever we require the reaction condition, as the reaction should not interact or interfere, the moisture should not interfere the reaction, in that case we can use this PF6 minus as the one of the ion for the synthesis of ionic liquid. Similarly, that BF4 for moisture stable but the water miscible ionic liquids, depending on the ratio of ionic liquid, the water system temperature as well as the alkyl chain length in the cation can alter, and we can synthesize the variety of ionic liquids which can be used in the various synthetic procedures. Apart from this, the few anions are also there which are less commonly used, but still they are having the very good effect in the synthesis, like triflate, nonaflate, and all these examples of this less commonly used anions in the synthesis of ionic liquids. Now, as we are saying this ionic liquids, it is not the completely new term. The ionic liquids, the research has been done from long back ago. So this ethyl ammonium nitrate, which is the liquid at room temperature, it was the first described in 1914, was considered as the first ionic liquid which is having the application in the synthesis. So in later 1940s, N-alkyl pyridinium chloroaluminate was studied as electrolytes for electroplating the aluminium. The first example of ionic liquids based on the dialkyl imidazolium cations were reported in 1980s, which is the nowadays also most widely uses dialkyl imidazolium and pyridinium cation is used, considering the less toxicity as well as the recycling is easy. They contain the chloroaluminate anions and prove to be useful catalyst or the solvent for the Friedel-Crafts acylation reaction. As we all aware about the Friedel-Crafts acylation alkylation reactions, so in that this dialkyl imidazolium cation can be used as one of the reagent, because normal Friedel-Crafts acylation we are using AlCl3 or FeCl3 because it requires the Lewis catalyst. So we can replace that Lewis catalyst or Lewis acid by using this ionic liquid as the salt. So as I said that it is not new concept. So day by day the role of ionic liquids in the pharmaceutical field is also much more seeking attention in the synthesis of various, not even in the drug synthesis, but in the various processes also. Some of the ionic liquids are also used as the nanocarriers. They are used in drug delivery systems such as media, formulation component, or the as the plasticizers. They are also used in the API synthesis, like ionic liquid itself can be used as a solvent, or it can be used as catalyst, or it can be used as reagent. If the reaction is enzyme catalyzed reaction, then we to stabilize that enzyme we can use the ionic liquids. Then for the crystallization of APIs, that is for the isolation, purification, and to select the crystal habit, whether the amorphous or whether the crystalline, for that also we can use the ionic liquids. Also, the ionic liquids has the biological application. Also, some of the ionic liquids are having antimicrobial, antioxidant activity. And also in the drug formulation, so as I said that ionic liquids can be used as solvents, co-solvents, or it can be used to increase the solubility of drug. That is also the application of your ionic liquids. So overall, the ionic liquids are having the, what you can say, we can use this ionic liquids in the various pharmaceutical applications. So there are various types of ionic liquids based on whether which type of cations we are using, which type of anions we are using. So it can be chiral ionic liquids if we have to carry out the chiral reactions and we want the specific type of isomer in the synthesis. Like for example, few isomers are active. Example like levocetrizine. So we want only the levo isomer, not the dextro. So for such kind of reaction where we want the chiral isomer R or S isomer specifically for any synthesis drug, we can go for the chiral ionic liquids. Also, we can use the polyionic liquids, then bioionic liquids, energetic ionic liquids, neutral ionic liquids, protic ionic liquids, supported ionic liquids, basic ionic liquids, and the metallic ionic liquids. As I said, it is simple the combination of cations and anions. So we can change their medium from acidic to basic simply by changing the concentration, but obviously the temperature and the state of that ionic liquid may change. So it may vary. Now, what are the important properties of these ionic liquids? Ionic liquids have the high conductivity. They are non-flammable, non-volatile, which is the problem of other volatile organic solvents which we are using. Then high thermal stability, wide temperature range for liquid phase. As I said, -40 to +200 degrees Celsius, it will exist in the liquid phase. So wide temperature range we can get for the designing any synthesis procedure. It is highly solvating, but not, it is non-coordinating. It will not form any coordinate bond with the reactive reagent. And also it is a good solvent for many organic and inorganic materials. Now, how to synthesize these ionic liquids? Because whenever we are using these ionic liquids in this synthesis, we cannot keep these ionic liquids prepared as such and then after 1 month or 2 months we can use. It's not like that. We have to freshly prepare these ionic liquids and then we can use these ionic liquids during the synthesis. So how to synthesize these ionic liquids? So there are two methods, that is direct quaternization and indirect quaternization. Direct quaternization means, as the name itself gives the idea, quaternization means we have to form the quaternary ammonium ion, or you can say the positively charged species we have to form. So this is the general procedure for the ionic liquid synthesis. So as you can see, NR3, we'll consider this R as it can be H, it can be any substitution, either it will be alkyl. So it means, suppose say for example, we are synthesizing the ammonium salt or ammonium cation as the ionic liquid we are using. So how to synthesize that ionic liquids? So in the initial step, what we can do, the quaternization of amine or phosphate we can use in the synthesis of cation. So in case where it is not possible, the quaternization is not possible, we can use the two different terms. As you can see here, the step 1 is your quaternization, okay, where simply we are forming at the valency of nitrogen, we know that it is 3, so it is Nr3, and when we add the alkyl halide to it, so it is converted into its quaternary ammonium salt. So that is the first step, quaternization. Then in the synthesis, the first we can add this. So two different paths can be used for the synthesis of, either by using with the Lewis acid, or we can use the metal salts, Bronsted acids, or the ion exchange resins in the synthesis of this quaternary ammonium salts, and also combining with the anions to form the liquid. So let's take one example. As I said that imidazolene is considered as most widely used the ionic liquid, which is called as DMIM-BF4. This BF4 is coming from the ionic species, and your DMIM is coming from your cationic species. So let's see how it has been synthesized. So suppose we are taking 1-methyl imidazole, okay. This N-methyl imidazole, when treated with alkyl halide, it will form its quaternary ammonium salt, that is 1,3-dialkyl ammonium or dialkyl imidazolium halide. So its salt is there. Now this cation or the salt, when treated with sodium borofluoride, then it will form its salt, that is 1,3-dialkyl imidazolium BF4, which is the ionic liquid. This can be used in the synthesis. So as you can see here, the image shows that in the ice bath, being this reaction is exothermic reaction, so we are using the ice bath. In that we are mixing this alkyl halide and 1-methyl imidazole to form this 1,3-dialkyl imidazolium halide, which can be isolated by the solvent evaporation process. We can evaporate the excess of solvent and we can get this salt. This salt then later on treated with the acetone. In that we are adding this sodium borofluoride, and then by mixing this salt with anionic reagent, it will convert into the ionic liquid, that is 1,3-dialkyl imidazolium BF4. Okay, that is the short form which is used, or the standard abbreviation which is used for this is DMIM BF4. Okay. And whatever the side product which is there, that is NaX. So that NaX can be simply removed by filtration process. So whatever the ionic liquid we get, so this ionic liquid, as I said, the synthesis, we can use the one method as I already said, but apart from that, we can do the synthesis of ionic liquids by microwave assisted method or ultrasonification method, microreactor, or task special ionic liquid we can prepare. Means suppose for example, any specific reaction is carried out at specific temperature and we require the chiral ionic liquids. In that case, we have to use the special procedure for the synthesis, so we can optimize that procedure and we can use. And after the synthesis of these ionic liquids, we have to purify these ionic liquids first. So that is the purification. So how to purify this? Either by using recrystallization, or we can use the chromatographic techniques, that is column chromatography we can use, or zone melting, or we can use the distillation process. And whatever the liquids we are using, these liquids later on, as I said, you can use this in the synthesis, and then you can separate it out, these ionic liquids, and you can recycle and reuse again. So how to recycle that? The recycling can done by magnetic separation or adsorption or distillation or aqueous biphase system and the membrane separation techniques you can use for the again separation of these ionic liquids which are used in the one synthesis process, and then again we can recycle and take again in the synthesis of the another product. As I said that room temperature ionic liquids, there are the two types. That is, either it will be organoaluminates, that means it will contain the organic compound which is fused with the aluminum salts, and the air and water stable ionic liquids. So we'll see one by one. So organoaluminates means, again I have taken the example that is imidazolium ion only. So since organoaluminate ionic liquids have the donor as well as the acceptor pattern, okay, so the Lewis acid can be acidity can be modulated by a simple relative amount of aluminum compound, that is whatever AlCl3 we are using. Okay, so acidic or basic ionic liquids can be attainable, as I said, simply by varying the concentrations of the species. If we want the ionic liquid as basic, then we can use the anionic species more. If we want it in the acidic state, then we can use this cationic species more. So based on the requirement, we can change the synthesis procedure or the concentrations of the cations and anions. So basic haloaluminates intercept the solvation and the solvolysis of the metal ion species. So as I said, this is the representation that if we change the concentration, then how the melting point is varying, because as I said that as you go on changing the concentration of cations and anionic phase, the temperature will vary and the melting point of these liquids will also vary. So this is the example. So large electrochemical window for both chloro as well as the bromoionic liquids is there. The advantage of this controlled Lewis acid ionic liquids, it is used in the Ziegler-Natta type catalytic reaction, which is one of the green chemistry reaction. But the disadvantage of this organoaluminates is, that is whenever we are using aluminum chloride as the salt, the disadvantage is it is moisture sensitive. So in that case, whenever suppose we want to control that parameter in the synthesis, then we cannot use these organoaluminates in those kind of synthesis. Second type is ambient temperature, air and water stable ionic liquids. So these liquids can be obtained by substitution of halide ions with 1,3-dialkyl imidazolium cation. Okay, with the other coordinating anions, weakly coordinating anions, because your chloride or halides are strongly coordinating anions, so that's why there is a problem of moisture sensitivity. So if we want to make the ionic liquid water stable, then we can replace these halides with the other reagent. So in order to be liquid at room temperature, the cation should be preferably unsymmetrical, and the melting point is also influenced by the nature of anions. It can be used for the immobilization of transition metal catalysts as the precursor in the biphase catalysis, as well as due to their inherent ionic nature, the ionic liquids can effectively stabilize the cationic transition metal, especially which are known to be more attractive than their neutral analogs. So mostly we are using the basic anions. As I said, that melting point is influenced by the nature of cations and anions. So as you can see, this is the imidazolium ionic liquid, imidazolium cation containing ionic liquid. And if we go on changing this X as well as the R, okay, so the melting point of these liquids are changing. So as you can see, for example, if we are using R is methyl, that is N-dimethyl imidazolium, and the halogen is chloride, so its melting point is 125. And if we replace that with BF4, okay, so its melting point is only 6 degree. So likewise, if you go on changing the substitution, N substitution as well as the salt parameter, means cationic portion and the anionic portion is changing, so the melting point of that ionic liquid is changing. Apart from that, we can also divide this into the protic and aprotic type of ionic liquids, again depending on the reaction condition, whether we want to use the protic solvent or non-protic solvent or the aprotic solvent. So based on that, we can synthesize or we can use this ionic liquid. So the example of protic ionic liquid, that is, for example, we are using ethylamine, which is, if it is treated with HNO3, so it is getting ethyl ammonium cation and NO3 minus. So this is what your protic ionic liquid. And aprotic ionic liquid means where the proton is not present. So that proton can be replaced with the or substituted with the alkyl substitution, and we can get this aprotic ionic liquid. So this protic and aprotic ionic liquids can be used depending on the requirement of the synthesis. These are the few common ionic liquids and their abbreviations. If you refer the papers of green chemistry synthesis, in that you most of the times you come across such terms, that is EMIM or BMIM. So what exactly these are? So these are nothing but the catalysts or the ionic liquids which are used in the synthesis, and their respective anions can be used in the preparation of the ionic liquids. These are also a few other examples, like anions we can use chloride, bromide, BF4 minus and so on. While the cations you can use like imidazolium, pyridinium, and many the heterocyclic cations we can use. But most widely used, as I said, is the imidazolium ion, and their respective salts can be used as the ionic liquid in the various synthetic process. Now, if you look at the development of ionic liquids, so it is divided into the first generation, second generation, and third generation, considering the pharmaceutical application. So the first generation ionic liquids which were used, the problem of the advantage of those ionic liquid is the high thermal stability and the low volatility. But the disadvantage of this first generation ionic liquids was they were sensitive to air as well as water. So they are moisture sensitive. So to overcome that problem, then they have switched to the second generation ionic liquids which are stable to air and water. But again, the drawback is they are having the high toxicity and the reduced biodegradability. So again, to overcome this problem, the third generation ionic liquids are now being used, which are mostly hydrophobic in nature, and their advantages, they are having the low toxicity as well as the high biodegradability, and these are having the most widely used you can say application in the many drug synthesis. In the further slides we will see the few drugs which are also synthesized by using the ionic liquids. But the disadvantages, they are biologically active ionic liquids are less appropriate as the solvent. As I said earlier also, that ionic liquid itself can also has the antimicrobial activity or some biological activity is also there. So if those ionic liquids can be used as a solvent, then there is the limitation in the biological activity, so that we cannot use. Now moving towards the application of ionic liquids. So as we saw the various properties of ionic liquids and the lot of you can say the volatility is less, as well as they are non-flammable. So ionic liquids attract the great attention in many fields, which includes the organic chemistry, electrochemistry, physical chemistry, as well as the engineering, as the reaction medium for the synthesis as well as the catalyst. In the electrochemistry, that is in the batteries also we can use the ionic liquids in separation process, as electrolytes in solar cells, as lubricants, as propellants in small satellites, as well as the matrices in the multi-mass spectroscopy, as well as the applications in many other areas, especially in the pharmaceutical industry. So why we are considering this catalyst ionic liquid as the catalyst? Because it is having the these catalysts are homogeneous catalysts, so they have essentially no vapor pressure, which facilitates the product separation by distillation. These are they are able to dissolve a wide range of organic as well as inorganic and organometallic compounds. So solubility, it enhances the solubility of the compound, and that property can be utilized for the dissolution to increase the solubility of the many pharmaceuticals. Then solubility of gases, for example, hydrogen, carbon monoxide, oxygen is generally good, which makes them attractive solvent for the catalytic hydrogenation, carbonylation, hydroformylation, as well as the aerobic oxidations. Apart from that, the polarity and hydrophilicity or the lipophilicity of these molecules can be readily adjusted by simply suitable choice of cations and anions, and the ionic liquids have been referred to as the designer solvent. As I already said, that depending on the requirement for the synthesis, we can change the polarity easily. We can change the hydrophilicity as well as the lipophilicity of the ionic liquids. Apart from that, they are immiscible with some of the organic solvents such as alkanes, and hence they can be used in the two-phase system. This gives rise to the, that's why this is used in the separation process. So this gives rise to the possibility of the multi-phase reaction procedure with easy isolation and recovery of the homogeneous catalyst. They are often composed of weakly coordinating anions like BF4- and PF6-, and hence have the potential to be highly polar yet non-coordinating solvent, and they can be expected to have the strong rate enhancing effect on the reactions involving the cationic intermediate. As I said, the most widely used that chloroaluminates can be used in the synthesis process. So considering the wide application, so I've just taken the few examples, the reactions which I've already studied in the second year as well as in the organic chemistry in SEM 3-4. So the diol-cellular reaction which we have already studied. So as we know that here in this reaction, this cyclopentadiene, when treated with methyl acrylate, so this reaction has been reported, and here in presence of ionic liquid, these are the various examples of ionic liquids they have used, okay, and these are the reaction conditions, whether basic medium or the acidic medium they have chosen, that has been given. And the product which is now, as being it is the diol-cellular reaction, so it is going to form a 6-membered ring, okay, bridgehead system it is there. And as in the bridgehead system, there will be two types of product will be possible, whether it is in the endo form, it is exo form. Endo form means where your COO CH3 that will be axial to this ring, and exo form means it is equatorial form. So as we know that in the diol-cellular reaction, always we get the mixture of products. So in order to attain the what you can say one product in the prominent concentration, we can use this ionic liquids. So here the reaction time is also changing, as well as the yield which is obtained in the whether it is endo or exo, that ratio is been given. Like for example, if you see this EMIM Cl AlCl3, which is basic medium composition, 48% of AlCl3 they have used. Time required is 72 hours, but you are getting 95% exo product and only 5% is the endo product. So you are getting major product as exo product. So based on the requirement, which form we want, whether endo or exo, depending on that, we can go on changing the concentration and we can get the stable product. So the advantage of using this ionic liquid in this diol-cellular reaction is it is having the endoselectivity, highly polar solvent, increases in the rate of reaction, it allows the water sensitivity reagents to be used, simple workup is there, and this ionic liquid, most important is it can be reused and recycled. Similarly, another simple reaction, that is hydrogenation reaction, as you can see here, this double bond is converted to single bond. Okay, and here you are getting the chiral center. So by using this ionic liquid, you can get the specific isomer, that is only the S isomer as the prominent you can say isomer in the synthesis. Again, the advantage is simple workup, two-phase system can be used, and again this catalyst can be reused and recycled. Next reaction is Heck reaction, where we are using the palladium catalyst, polar solvents such as DMF and the acetonitriles are employed, and the aryl iodides are normally used as the substrate. In case where the less expensive but the less reactive aryl bromides or the chlorides are employed, and it is necessary to use more active catalyst or add the phosphine ligands in order to retain this catalytic activity. So by utilizing this 1-butyl 3-methyl-imidazolium bromide as a solvent, these aryl bromides react easily with styrene and gives you the stilbene as a product. And as you can see here, if you change the halogens, like if it is iodide and your R is H, then you get 100% reaction. Okay. Advantages: it is less expensive, high yields, then polar solvents, expensive, and the phosphine ligands, and this is without the phosphine. So these are the advantage of your the liquids, ionic liquids, which are overcoming the problems with the conventional method. Then carbocation chemistry. Again, as I said that ionic liquids containing chloroaluminate anions are the strong Lewis acid, and if the protons are present, then we can say that they are the superacidic in nature. So these ionic liquids are used as the solvents as well as catalysts, basically in the Friedel-Crafts alkylation, acylation, as well as the arene exchange reactions. Simple example of Friedel-Crafts acylation. Again, the yield is 64% in the acetonitrile, but here this regioselectivity is there. That is, we are getting only the orthopara ratio is 93:7. While we are using this, whenever we are using this ionic liquid, we are getting only the this synthesis product. The reaction is regioselective, and it is the product is in the high quantity. Then next is same Wittig reaction. Again, the ionic liquid is advantageous here also. Again, there are the two possibilities, whether E or Z isomer. So here we are getting E isomer as the prominent product. So apart from that, the many other reactions are also there where we can use these ionic liquids as the medium for the synthesis, that is hydrogenation, hydroformylation, epoxidation, and the many green catalytic reactions like Suzuki coupling, HKR reactions, and so on. So these are the few reactions which we can, in which we can use these ionic liquids as the solvent. Another example in the synthesis of heterocycle, that is the pyrimidine derivative synthesis, where we can use this L-proline nitrate as the ionic liquid in the synthesis of this pyrimidine nucleus, where we are using this thiourea, substituted aldehydes, and ethyl acetoacetate. In presence of this ionic liquid, that is L-proline nitrate, we are getting this pyrimidine derivative. Means this just have taken one example for pyrimidine synthesis, but similarly we can use these catalysts for the synthesis of many heterocycles. As I said, these ionic liquids have the wide application. So it can be used as the separation media. It is used as liquid membranes in the extraction procedures as well as in the carbon capture. It is used in the electrochemistry, that is, it is used as the fuel in the cells, batteries, sensors, metal plating, as well as the solar cells. It is acting as the fluids in the heat storage, lubricants, as well as surfactants. It is used as green solvent, especially as the biocatalyst, then chemical processing. In protein crystallization, these ionic liquids can be used. And it is also used as the advanced material in the liquid crystal display as well as the in the various pharmaceutical applications. So as I'm saying, the pharmaceutical application, so it has the biomedical application of the ionic liquids. So first is it enhances the solubility. It helps in the solubilization of drugs. So that is one of the area where these ionic liquids are being used. Second is active pharmaceutical, that is in the synthesis of APIs also, these ionic liquids are being used. In drug delivery process, ionic liquids can be used. As I said that if some compounds which are, there is a problem of bioavailability, we can use this ionic liquids, and this specific targeting we can achieve with the help of ionic liquids. Then These ionic liquids can be used as the nanocarriers for target drug delivery, protein stabilizations, whatever the crystal structure we are using in the molecular modeling. So for the protein stabilization, ionic liquids can be used. Some of the ionic liquids are having the antimicrobial property as well as they are used in the biosensing area. So as I said, these ionic liquids as the green solvent in the synthesis of pharmaceutically important compounds, being they are sustainable, recyclable, non-toxic and non-volatile. These are the few examples of the drug which are synthesized by using the ionic liquids, which having the various therapeutic category like antibacterial, antiviral, then your analgesic drug, anti-cancer agent. So these are the few examples by which by using ionic liquids can be synthesized and having the therapeutic application. So concluding this seminar, that is by considering the research which is going on and the many publications till date shows that if we replace these organic solvents by the ionic liquids, it can lead to the remarkable improvement in the well-known processes. As I said, the name reactions, we can change this volatile solvents by using the ionic liquids. Of course, there are certain drawbacks are also there, but if we do the research on that, then that can be overcome. And there are also indications that we can switch from the normal organic solvents to the ionic liquids, which will lead to the environment friendly reactions, and it opens the wide field to future investigation into this new class of solvents which is having the catalytic application. So these are the references. Okay. Thank you.
Thank you, Miss.
Good afternoon, everyone. I would extend my gratitude to our eminent speaker, Mrs. Deepali Nahar ma'am, for enlightening us with her knowledge. Today, Today's webinar gave us a deep insight on the topic role of ionic liquid in synthesis. Ma'am has focused on various points on how to consider, why to consider ionic liquids, what are the typical ionic liquids, what are its role in the pharmaceutical industry, what are the important ionic liquid properties, the method of ionic liquid synthesis, development of ionic liquid, and application of ionic liquid. We would now be soon continuing with another session. So please don't leave the meeting.